Assalamualaikum students. Welcome to DEM or Design of Electric Machines, but it's also called as the Electric Machine Design, EMD, or Design of Electric Machines. Both are interchangeably used. Uh, First of all, today we are actually going to talk a little about the course outline, the total hierarchy of this course, and then hopefully we are going to I'll talk a little bit about transformers, since you all know electric machines course and even this design of electric machines course, they are going to be having a lot of transformers and machines, because transformer is also a machine. And then three-phase induction motor we are going to talk in depth detail. But before I move on towards any talking about the transformers, let me just talk about a little bit on the the files. Okay, so the course outline. You have this course outline. You already have this course outline in your LMS over there. There are 4 CLOs for this course, and as you can see, the first one is actually the basic principles of magnetic circuits and the philosophy of the transformer design. Especially, one thing very important to learn in this course would be that any design can be the best, any design can be the worst, and maybe one design suits one manufacturer, the other design may not suit one manufacturer, solely because the other one is very cheap, the other one is very cost effective. But on the other hand, we are going to learn the trade-offs, which means that you are actually going to understand that by increasing the flux or flux density or maybe any other parameter, what benefit you are going to get on the cost side. I'm going to talk a lot about the cost also, because the competitive industry in Pakistan is mostly driven by the cost. So even in if you are a buyer for a transformer or any other device, you are actually going to talk a lot on the cost over there. So you are always going to go for the cheap solution, even if it is having less losses and less efficiency and whatever. But we will talk on that aspect as well, that those losses, they are actually going to give you a bigger penalty in the longer run, and that longer run is going to be how much years or whatever. So we're going to talk a little bit on the cost analysis also. I'm not a transformer manufacturer or something like that, but most probably will talk a little bit information I have from the industry. Then in the second CLO, we are going to talk on the core, the windings and the cooling system, which is very much important over here. So you are actually going to have the cooling system, which is actually the fans, the fins over there, the tank design, and certainly the windings is going to be a very important part of this course. And not just the transformer, we are going to talk about the induction machine windings also. I'm not going to go in very much in-depth detail because of the time constraints, and I will do like 2 or 3 types of windings and leave the rest for you to actually practices. And those of you who have been a fan of the winding diagrams in your machines course, the lap winding and the wave winding, you're going to have a something similar like winding structure over there, but a little bit difficult design. As far as the plotting is concerned, it's almost the same. Then the third CLO is about the rotating electric machines over there. As you can see, it's about the design parameters. We will follow the design of an induction machine first, and then we will translate it to the 3-phase BLDC also, which, or you can call it a 4-wire or a 3-wire BLDC, brushless DC. This change will be incorporated inside this course outline later on. The fourth CLO is for actually a teamwork or a team development, so that you can actually, and that is actually going to be most probably being done in the complex engineering problem of this course, and that will be done for the lab also. So the complex engineering problem, as you can see over here, this one CEP, this is going to be done in the lab also. There are going to be 4 quizzes. As you can see, there are 4 quizzes marked over here. The midterm examination is going to be 30, the final exam also 30. We can change this one later on and make this 25 and this 35, that's so on. And the CEP and assignments are also going to be a very important part here. The reason, because the assignments are going to be very much important for your understanding, and they will include some numericals also, that will be design problems, and secondly, they will be having some open-ended problems which are not even in your course book or any of the materials of this course. So that will be very important. Then coming on to the The next one over here, you have the weekly over there. I'm not going to discuss all of them over there because this is a whole lot of things. So the weekly RAM is there. The only change which is going to be done a little bit in this course is actually going to be this 2 over here. These 2 weeks are going to be replaced by BLDC, which means the brushless DC. So hopefully we will talk about the brushless DC when we have discussed the 3-phase induction machine. Over here you can see I have the winding designs being covered in 1 week or something like that, but maybe we will try to elaborate it to like 1.5 weeks or 2 weeks, or maybe I will split those lectures in 2 or 3 different parts, maybe as recorded just like this. As far as those courses concerned, on my YouTube channel you also have the previous year recordings also available for all the course over there. Maybe if I miss something because of some human error, you can even consult those videos also. But almost I'm going to cover almost the same course, just a little bit addition this time, that instead of this one I'm going to discuss the BLDC, that is the brushless, because the recent innovations in the electric car are actually now going to make this as very much important for the design of a brushless DC. So not in-depth detail because 2 weeks is not that enough, but still anyway we will talk about a little bit analysis or a brief analysis how that design has to be done, so that design process. Coming on to the lab for this course, if you have seen the lab over there, the lab is going to be conducted also for this one. It's a 1 credit hour lab. I guess it has been wrongly written on the LMS that it is 3 credit hour. There is no lab in engineering which is of 3 credit hours. So this is actually a 3+1 course. So don't worry on this. This is a 3+1 credit hour course. Certainly 1 is for the lab and the 3 is for the theory one. Now the lab actually, since this is a design course, okay, whatever you design in the theory, practically it has to be implemented there. But since any transformer design or any induction machine design, that is going to involve a lot of cost. Even no lab in anywhere in the world for undergraduate class can actually do a design. So I have bifurcated the lab overall. So whatever lab you are going to do in this course, the lab is going to have 3 components over here, which we are actually going to do, and I will just share with you the lab first component, and certainly it will start after like 1 or 2 weeks of the initial labs over here, because when we have done some design in the transformers, then we can do that. The first portion of the lab is actually to develop a software or an Excel flow chart. So either because Excel is very simple, and or a program, I will strongly recommend some programming language, maybe MATLAB, with a little bit GUI if possible, if anyone, not a restriction, but at least some developing an Excel or some programming for the design of transformer. This is very much important. When we will do the design of transformer, we will talk in much detail that which parameter has to be selected. So we can develop some Excel sheet over there, so that you just have to give the numbers and you don't have to do the mathematics yourself. That mathematics will be done by that Excel sheet or whatever drop down boxes you are going to select or check boxes, and that will be done. So this is our first part of the lab, and this will be covering approximately 1/3 portion of our lab, and this has to be done individually. This is an individual work, so whatever students are you there, that will be actually done. The second task would be that you have to actually design and manufacture. This is actually going to be a little hardware work involved over there, but you will love this work because whenever you have a transformer, you need to open a transformer, you need to make it, you need to wind it, and you have to design and manufacture a small approximately like 15 to 50 VA transformer, and certainly this is going to be a 50 hertz transformer, and certainly we will discuss on that voltage levels also. So basically the second portion is this, that you have to actually stack up those EI cores, and so supposedly I have this EI core over here, and this is my EI core. I have just made it over here. So you are going to stack up these cores and you are going to do the windings. I will tell you the design equation of this transformer, and I will tell you the design procedure. So each one of you has to make a small 15 to 50 VA transformer, and for this purpose the maker's lab in the ground floor in the lab is going to be used for this purpose. We have a winding machine over there. It is by normal hand, but if you have a large number of tons, then maybe we can arrange some electric machine over there. But you have to do that winding in that lab. Certainly you're going to use the copper or whatever you want to use, aluminum over there, that's totally up to you. But whenever you are going to design it and you are going to manufacture it, you are going to run it at whatever that voltage may be. Supposedly one voltage which I am more interested in is from 220 volt to approximately 48048. Now why I'm interested in this voltage? Because this 48048 means that this transformer can be used also as an inverter, so a small mini inverter. So many of you who have done power electronics, you must have worked on some sine wave inverter or something, and afterwards when you have converted into a 48 volt sine wave, you want to step it up to 220 volt, and maybe that transformer can work as your portable. But the design and manufacturing is not just going to be the part of this. The second thing is this, that you are actually going to do the short circuit test plus open circuit test of this transformer in machines lab. I will make this possible that lab equipment which is required for the short circuit plus open circuit test can be brought in maker's lab. So each one of you, whoever you are going to design, we are going to evaluate you on that design, also the design report, the transformer which we have winded. Certainly you will see that design also, and secondly we are going to see the cost analysis of that transformer plus the size analysis. This is very important. So this is not like this that you want excellent open circuit test results, you want extreme best short circuit test results, and you say, okay, I'm going to put in a large amount of money, like maybe like 4,000 or 3,000 rupees for just a simple 50 VA transformer. You will get the best thing, but I will see the size and the cost of that thing. So that is also going to be an elevated parameter. So you're going to do this by hand. It's a little messy work because of that resin which is involved in the windings and the lamination, especially over here. This lamination, this can be EI, or this can be, let me just keep it as EE. So we normally keep it as so this can be EI or EE. This is totally up to you. So this can be just like I have drawn this EE, or this can be, so these are stampings. So this is the same EI core. This can be also made as something as this one. So this is also a type of core which you will find most probably at Hall Road, and this is the other shape of this one. The other shape is something like this. This one is called as FF. Now this gap over here, this gap I have kept deliberately, so please don't worry on this one. This gap over here, I have kept deliberately this gap. Otherwise I could have shown it as combined together, but this is an FF core, this is an EI core. It can be UI core also, but this is a shell type transformer. I will come back to this a little bit just now in the next few minutes. So you're going to get either EI or FF core, and then you are going to design this core. So the higher the size, certainly the cost is going to be the more, the size is going to be the more, even if you get the better results for your short circuit and open circuit test. So we are going to evaluate it. The third thing which is going to be very important, and that can be very good for maybe some of you are working on some of your power electronics FIPs also. The third thing is going to be designing high frequency DC to DC converter. So designing a high frequency DC to DC transformer, you can call it. It's not going to be a converter that MOSFETs or whatever, we are going to give you that. So the point is this, that I am going to actually tell you that you are going to design supposedly a 50 VA transformer at 50 Hertz, and this one which we are going to design it, it's going to be something at 100 kilohertz plus. So we will see the design is how much different, which means that the 50 hertz design will be approximately like 10 times greater than what you are going to achieve in high frequency transformer. Certainly it's not going to be working at sine wave, and it's going to be using a ferrite core. So those of you who are interested in this one, certainly it does not come in the scope of this one, this course over there. But since we are designing the transformers, and these two examples over here, these are going to actually tell you a very decisive decision on this one, that you are having how much losses inside your transformer for a 50 VA one over there, or even if it is the small one that is actually working at 100 kilohertz. So these are three components of the lab. So the lab is going to be not some experiment based or normally some lab manual based. It's actually going to be three tasks over here. The first two tasks we will be assigning you before the midterm. The last task, when we have done the transformers and we have done that high frequency design part, which we will do in the lab work. So this is the whole nomenclature of the lab. Very easy lab, not that difficult. So you will learn and actually have some fun doing some work on this one. So this is the whole nomenclature of the lab. Then coming on to how this course is going to go on. Now, one thing very, very important, I will be giving on this on the same pad over here using this pen. So these lectures will be available in recorded form on my YouTube channel. And as you all know, you have studied machines with me. So certainly you have an idea that I have already my website over here, ep.nge.com.pk. So everything related to this course, the links of these videos over there, or any assignments or any quizzes, or even the previous midterm results or whatever, they are available on this one. I guess it's still updated for your session, but even if there is some anomalies, most probably they will be covered in the first week. And those of you who don't have that prerequisite passed at present, I will strongly advise you to unregister it, because the semester cell is going to actually unregister you in like 1 or 2 weeks, because this course has to have the understanding of the machines. That is very much important. So without machines course, it's very much difficult to understand this course, because today's lecture I'm going to talk a little bit into what you have studied in your machines course, and then in the next lecture we were going to actually make those as the basis and then design the first transformer equation. I'm not going to write that equation just now, because that's going to create a problem over here. I'm just going to limitize myself today for whatever we are talking here, the basics of transformer. You have read this transformer very carefully and very much from your first year in your FSC also, in second year also. So this equation, which you already know, that is V1 by V2 is equal to N1 by N2. So this equation, or it was in this form, that Vp over Vs is equal to Np over Ns. This equation has already been there with you. Now, I have prepared a set of questions over here. I will make that file available on my website also. It has some questions, like maybe 20 or 25 of those questions, and I'm going to discuss them. Some of them I'm going to discuss, some of them I'm going to leave on you. The first question over here, that what is the difference between the core type versus the shell type? So core or shell type? This is a normal question. Every time this is asked over there, that what is the difference between a core type and a shell type? Shell type over here, it has an L over here. Now, when I'm talking about the core type or the shell type, this means that I'm talking about the core type, and I'm supposingly I'm talking more on the single phase type, supposingly. So this is going to be my, so this is going to be my core. So okay, so this is my single phase core type, and on this one, supposingly this is my winding which I am doing. I'm drawing a two-dimensional picture. This is not a three-dimensional picture, and you are familiar with this one very carefully up till now. And I have drawn this one by two windings. One is on one limb. Now over here, this is very important thing, that this is called as, if I mark it supposingly by this one is and this one, these both are called as the limbs of your transformer because the windings are done on this one. And this is the single phase core type transformer. So this is a single phase core type transformer over here. And certainly, actually one thing very important, since you're going to design cores over here, there is no concept of high volt primary winding or secondary winding. Why? Because you can energize your transformer from here and get an output here, or you can energize your transformer from here and you can get your load attached here. So there is no concept of primary or secondary. This is very important. So this equation, I'm not going to use it. Yes, I'm going to use this equation where 1 and 2 are subscripts which are going to be representing the high voltage side and the low voltage side. So there is no concept of primary winding and secondary winding. Yes, I am going to call this one as maybe like as V1 the output, and this one is V2, that is the output. And certainly they are going to be high voltage winding and low voltage winding unless and until you have a 1-to-1 ratio transformer. So these are the two limbs. This is a core type single phase, this is a single phase core type transformer. And then certainly this portion, let me make this over here. This is that core. Okay, this is, sorry, on this one, let me just rub it. Sorry. Okay, so I have this one over here, and if I just remove it. Okay, so this area, just listen, see this one very carefully, where I am highlighting this one, and certainly this one. This one is the yoke of your transformer. If you remember what was the yoke of your transformer, the yoke in a DC machine supposedly was the flux completion path. So this was the yoke of your transformer. So the yoke is actually completing the flux path. Now I have asked this question also in your machines course sometimes back, if you remember it, and I have talked in much detail on this one, that supposedly I have a simple core, and on this core I have a winding done on this. Supposedly this is my one winding, and the other winding is done on this one. So this is supposedly, you can call it, this is V2, and you can call it supposedly V1. Will this transformer work? The question. In principle, yes. Why? Because these two windings are coupling each other over here. But the problem would be that since supposedly you are applying a source over here at V1 and you want the flux to be moving towards V2. So what happens, supposedly depending upon your direction of current over here on this one, you want your flux to travel through air and then complete its path, supposedly same like here over here. So what has happened, air is a very bad medium for flux over there. So this is practically not possible. So the reluctance is going to be so much. This is a very important one. The reluctance, which is given as reluctance units over here, this reluctance is going to be so much that the flux is going to be very, very small. And when flux is going to be very, very small, any change over there is not going to be possible. So we all know V2 is going to develop a voltage that is going to be defined by N d phi by dt. So when d phi is not there, when flux is not changing, it's not even there in very small Webers over there. So V2 is not going to be induced. Or even if V2 is going to be induced, now this is a very important one. Even there is a small change, supposedly what I meant by this one, if you had a flux over there and this was changing like this very one over there, you are going to get some voltage V2. Yes, there will be certainly some voltage. But when you are going to connect a load over here, it will not work. Why? Because the current is not going to increase, because you are not going to have any other power transfer, because how the power is transferred from one winding to another? Through the core. The core is actually the medium from where, because in a transformer, you convert your energy from electrical energy to magnetic energy, and then you convert back it into electrical energy. So now this medium has air. So practically this thing is a transformer. theoretically, but practically it can never work. Okay, coming back to our core type and shell type transformer, because then the discussion is going to go anywhere else. So over here, I have the core type transformer drawn, and if I draw a shell type transformer, the shell type transformer is very also important. So, and this is the same transformer you normally get from haul road. The normal 15 volt transformer or 20 volt transformer you get from haul road for your power supplies or any of the projects or something like that. So the transformer which you have over there is now the only change in a shell type transformer is this, that there is a central limb, and that is approximately now this is actually a little away from what I wanted. Let me just again make it. So okay, this is still not the very best over here. Actually, I'm using a different color over here. So okay, I guess now I'm almost there. So this is my shell type transformer. Now over here, this is very much important. If you're here, if you are seeing it, the winding is going to be done on the central one. This is my V1 winding, and V2 winding is going to be done here. This is V2, and certainly this is V1. So this is a shell type transformer, and the yoke portion is over here, this portion. All of this is the yoke portion. Now you may argue why we have not done the winding on here, here and here. If we had done the winding on these two, this was a core type transformer. Here, this is a shell type transformer. This is a shell type, sorry, on this one. Come on. So this is a shell type transformer. And on this shell type transformer, you are having a single phase, and here V1 and V2, which are actually the windings voltages, which can be on from N1 and N2. I'm not classifying them as high voltage or low voltage. We will discuss them in the next lecture. So V1 and V2, they are more closer to each other, so their coupling is better. If you remember your CAD course, there was a coupling coefficient. There was a coupling coefficient, and that factor was called as K. So in shell type transformer, this can be something like 0.98. I'm just assuming, I'm not giving you a value. Okay? This is not a value over here. I'm just giving you example. And for a core type transformer, maybe this is like something 0.92 or 0.95. So in shell type transformer, you have a better coupling as compared to the core type, but their heating is going to be difficult to dissipate. Why? Because here the windings are surrounded by air, or maybe it's going to be surrounded by oil or something like that. So it's not going to be very good for the cooling of a shell type over there. We'll discuss them later on in very much detail. Now the transformer which you normally get at haul road, because of its size constraints and good coupling, this is the one you get from haul road over there. And then we will talk about the different designs also over there, because this is a shell type transformer, not just like the one winding is done over here, the other winding. You have different parts of the winding sketched together, which means that V1 and V2, the N1 and N2, they are submerged together. So it's like just like a sandwich winding. This is a type of winding in shell. We will discuss them in much detail. So this is the core type and shell type transformer over here. Now coming on to a three-phase. How these transformers are three-phase over here. So this is going to be, let me just rotate this page. Okay, so a shell type transformer, in fact, let me just import a small picture over here. This is a simple picture I have taken from Google Images, and I hope you can see the three-phase transformer very carefully over here. And in this diagram, you can see the same single-phase core type. This is the same single-phase core type I just drawn above. This is the same shell type transformer. A three-phase core is going to be having three limbs, and on each one of them you are going to have the 3 phases. So this means that if I just go a little bit zooming in this one, so if I have this first one, so this is going to be the first N1 winding, the second winding is going to be just below that. Or maybe they are going to be done above each other, which means the whole yellow winding covers the whole limb, and then the red color winding is being done on that one. So these are the first phase. This is phase A, this is phase B, this is phase C. And similarly, in a shell type transformer, just like this one, this is one phase over here, this is second phase over here, and this is third phase. Now, how these are used is a very important factor over here. Now, I told you this one is the same simple dry type transformer which you normally use for the Hall Road transformer, which you normally get is this one. Core type single phase transformers are used wherever the load is not that much. And this 3-phase core type transformer is the distribution transformers around you, or even in outside our department. There is a distribution transformer, or any other outside your home or any outside the factory. The 3-phase core type transformer is the normal transformer used for distribution. But why it's used, why it's not shell type is not used, the only reason behind it is that a shell type transformer has a poor cooling factor, because you can see the windings are jam packed around the cores around there, but it has a good coupling coefficient, which means it's going to have less losses, but cooling is not going to be good. So you can't run it for 24 hours over here. Why? Because you have to, if you want to run it, you have to employ more cooling tactics over there. So this transformer is actually used more. I'm not saying that confirmedly they are always going to be used for power and distribution. This is always going to be used as a power transformer. And what are power transformers for you who don't have an idea? Power transformers are those transformers which are used in at generating grid stations or at Tarbela, Mangla, wherever the transformers are going to be running when the generator is running. So those are power transformers, and the size is huge. I'm talking about something in megawatts. But for distribution transformers, the normal transformer you get around your houses are 400 kVA, 200 kVA, or maybe like 2500 kVA transformers are also used. And certainly they are placed in some tank, and then there is oil over there. So the cooling is done. So they have a good cooling factor, and you all know that distribution transformer outside your house or in your house lane, they are working 24 hours a day. So that's not a big issue over there. But power transformers, since you have to cool them with some certain parameters or some equipment, they can only be run for like 5 or 6 hours. So maybe if a Hubco plant or Capco plant generator is working for like 8 to 10 hours, then certainly this means that they are going to be running just for that much time, and afterwards you can cool them very easily. So they have their own issues over there. I will come back to the distribution and transformers a little later over there. Now, this is the same simple flux diagram over here. As you can see, there is a primary winding and there is a secondary winding. I'm not going to use this word of primary and secondary as I've told you. I'm only going to call it as V1 and V2. There is no concept of primary and secondary as such. So, one question over here. There are 2 types of losses inside a transformer. And what are those losses? One loss we already know is called as the core loss, and they are called as constant losses. Why constant losses? This is a big question over here. Now, where are these core losses happening? Certainly inside the core, which I mean by this one core over here. So I'm talking about this losses inside the core. And why they are constant? They are constant because the flux inside, now this is a very important part, because many of the students actually don't remember this, that the flux inside the core remains constant. Now, when I'm using the word constant, this does not mean that it is a DC constant. It's not a DC constant. It is an RMS constant. What this means, that when you have a flux waveform supposedly, and you have this flux waveform flowing inside this one, so it's going to have an RMS value. So it's having at some time when you are applying a voltage over here, so the flux are flowing over here, and then they are coming back from here, and then they are going over here. Since this is a shell type transformer, so they are going to be originated from here to here. So they are changing their direction after every half cycle, just like over here, this is the positive cycle, this is the negative cycle, but the RMS value remains constant irrespective of the load. So even if your load changes, you are not going to have any change in the RMS value of flux. The flux waveform, if I draw this one over here, the flux waveform is certainly in RMS changing over there, but the RMS value remains constant irrespective of the load. Now, why this happens? This is a very important point over there. So if I make, supposedly, let me change this rotation over here every time this has to, okay, sorry. Okay. Sorry. Okay, sorry for this delay. Really, it's not easy to actually use this one. Okay, now I'm talking about a transformer, and if I draw that transformer, supposedly again over here, now I'm going to draw it with some legible color, so it's actually easy for you. What I'm actually pointing out over here is this, that I'm drawing a simple single phase. So it's still not straight. So this is my core type transformer. I'm drawing this one. And okay, so I have the single phase core type transformer. I'm drawing one winding over here on this one. And I'm drawing the other winding, which can be the low voltage winding or the high voltage winding over here. So this is my, you can call it V2. And here I have my V1, and certainly I have supposedly attached a source over here, and this source is going to be attached over there. Now, when a source is attached, I have nothing load attached over there. So what happens? Current is flowing over here. Supposedly I'm talking the positive cycle over here. This is the current flowing over there. Because of this, the flux starts to flow, and this is the direction of flux flow. So this is the direction of flux flow. Because of n d phi by dt, we already know that, n d phi by dt, there is going to be a voltage induced over there. If I connect a voltmeter supposedly over here, I'm going to get that voltage over there. Now, when I will connect after this voltage, a load over here, what will happen? Before the load was connected, before the flux inside the core, that was flowing over there. It was having an RMS value, and supposedly that RMS value was 4 milliweber. I hope you still remember the units of flux, the flux density or flux intensity. Please revise those if you have not done that, or if you don't remember it, because in this course we are going to talk about all these design parameters over there. So those flux core is approximately 4 milliweber, and I want to actually now have a 4 milliweber flux flowing inside the core. Now I attach some load RL. What will happen? Certainly the current inside, since the flux is now flowing over here, what will be the direction of current? Now this is very important. Now all of you remember it. There is a Lenz's law. What was that Lenz's law? The Lenz's law was actually telling you that the current induced over here inside a circuit is going to be in such a way that due to a change in it, that when you are going to have a magnetic field because of that induced current, it is going to oppose the change in flux and exert a force. Now this is very important over there. Now what is happening? The flux is flowing upward to downward over here. If I just zoom into a little bit. So when I'm going to have supposedly a current inside this winding, that flux has to be produced in upward direction. And using your right hand rule, you can point out your thumb in the upward direction, and the fingers are curled in this direction. Actually, I should be using a little light color over here so that it's easy. So this is one over here. So the voltage or the current is going to flow from here and come back like this. Now what is going to happen? The load is connected. The current starts to flow over here. and supposingly you connected, I'm just going into the voltage values and all that stuff. Supposingly you connected a 100-watt load. Okay? This was the 1-to-1 ratio transformer with 200 volts applied over here, 200 volts applied over here. This means that approximately 0.5 ampere current was flowing. I'm taking it as a simple resistive load because this is simple RL. Now 0.5 ampere current is flowing over there. Previously, assuming that this was an ideal transformer, when load was not connected, the no load current of this transformer, if this was an ideal transformer, has to be 0 ampere. But we know this is not an ideal transformer. We are designing a practical transformer. So it will not be 0 amperes. It will be supposing like something like 0.5 amperes. Now, 0.5 ampere, where it was being consumed? It was being consumed inside the core losses to travel the flux inside the core with an RMS value. Now, when you attached a 100-watt load, a 0.5 ampere current has started flowing over there. Now, this current inside this one will increase to 1 ampere. Because this 0.5 has to flow from here. Transformer is not generating it. Transformer is just supporting it to flow from one end to the other. So, the flux inside this winding which is being produced. So, now the flux being produced by the primary winding, you can call it primary or you can call it phi 1. I'm just using phi 1 over here. And this winding is the second winding. So, this is going to be producing a flux phi 2. Now, the flux inside the core this time, which I am going to call as phi net, is equal to phi 1 minus phi 2. And because of that 1 ampere, supposingly that went down to approximately, for example, that went out to be 8 milliwebers and phi 2 is going to be 4 milliweber. So the net is still 4 milliweber. Because this flux is going to produce in from the left side to the right side at some certain instantaneous point. This flux is flowing in the opposite direction over there so that it opposes it over there because this is the Lenz's law. So certainly the net flux remains the same. This is very much important. I hope you understand this. And that's why the core losses inside your transformer, they remain the same. The core losses inside your transformer, they remain the same. Unless and until there is a little bit increase in the applied voltage, and certainly, yes, the no load current will increase because the core is going to have an inductance and it's going to have an inductance depending upon, I hope you still remember your machine's equation, that was L is equal to N square by reluctance. So you are going to have a constant reluctance unless and until because you are working at 50 hertz, so the reluctance will be normally same constant. So the number of turns are depending on this one. So there is going to be an inductance of the primary winding. In fact, I have also the habit of this primary every time because of the machine's course. So this will be N1 squared divided by reluctance, and similarly there will be an inductance of the secondary winding, that will be L2 by N2 squared divided by reluctance. The reluctance is going to be the common factor over here. This is very important because they are done on the same core. Okay? And then certainly there is going to be some mutual inductance also, which is going to come in the transformer equivalent circuit also. So I hope you have an idea what I am doing over here. So the transformer works at a constant flux. And I hope you now understand what is Lenz's law doing. And if you don't still remember it, I hope you can go on towards over there. Now, in this transformer over here, you have some leakage flux also happening. And where that leakage flux is going to flow, now this is very important. Leakage flux is that flux which is not linking the other winding, which means it's not flowing in the air. So leakage flux is that flux which is completing its path just like here. So this flux is going to be phi LP because it's not linking with the other winding. And similarly, the flux which is going to complete its path just through this one, remember, it's not possible that the flux will not complete its path. Just like any electric current, any magnetic flux has to complete its path. Ye nahi ho sakta ki this is going to flow and this die down. It has to complete the path through this one. But it's traveling through air, so its value is going to be small. So phi LP and similarly phi LS, they both are going to be also there, and they are part of the leakage flux. And those of you who still don't remember the equivalent circuit of your transformer, now I'm drawing the equivalent circuit of your transformer. Please revive all this stuff. I'm doing this one just to revise everything, whatever you have studied in your machines course. And I hope after this lecture, you can do this one very easily over here. So I'm drawing this equivalent circuit now, and this equivalent circuit is going to be like this. I hope you still remember your equivalent circuit. This is going to be my secondary winding, and this is the secondary winding. Okay, I'm not going to short circuit it. I actually made it in a short circuit way. So this is going to be my, and if I name them, this is very important. The naming is very important over here. This is my RP. This is my JXP. And this JXP, if you remember it, this is the same phi LP. So this was making it in series over there. So larger the current, the larger is going to be the leakage flux also. Similarly, this was RS and this was JXS over there. This one was R0 or RC, whatever you want to write, it's totally up to you. And this was JXM. And certainly this is the ideal transformer with a turns ratio of A/1. Okay, what was A? You can take it as N1 over N2. So this was the number of turns over here was N1 by N2. So if I mark it now, maybe like with some other color over here. So if you are going to connect a source over here, this source is going to be connected over here. The current that is flowing over here, I can call it I1. This current, if the load is not connected, is going to be I0. And in that case, I1 is going to be equal to I0, because that is the only current this transformer is going to behave as an ideal transformer. So I1 is equal to I current at no load. So the transformer is going to behave as just at no load. And when you are going to connect a load at the secondary side, so you are going to have a load connected over there. Supposedly this is a variable load. So this current I2 is now going to travel over there. And if you want to convert this transformer equivalent circuit into its referred side. Now please go through this one, referred side, very important one, because this is going to be also required in our calculations. So if I want to actually refer this circuit diagram or equivalent circuit actually in the second case, so this is going to be and here, since that transformer is gone, so I'm going to call it as simple. So this is going to be, again, if I again name it, this will remain the same because they are on the primary side. Since these both are referred from the secondary side, and I guess you remember it, that when these components are going to come on this side of the transformer, they are going to be multiplied by the square of the turn ratio on which side you are coming. So when this RS is going to come over there, it's going to be multiplied by A divided by 1 whole square of that person. So this means that this is going to be A square RS and this is going to be A square JXS. This one will remain the same, R0 and JXM. And for those of you who have still no idea that what is this R0 and JXM, R0 was the eddy current losses over there, and JXM was the magnetization losses inside the core over there. So certainly they both are going to be, the larger the value of R0, the lesser is going to be the eddy current losses over there. Certainly this branch current, we call it as the hysteresis plus eddy. This one is called as IM and the whole current is called as I0. For those of you who still have no clue what I'm talking about, if you have, supposedly this is the voltage phasor, this is supposedly, you can not call it V0 actually, let me call it just simply V1, applied voltage, assuming it. So the current vector is going to be, supposedly this is going to be I0. It's not going to be that much large. I'm just drawn it for your elaboration. So if I make its perpendicular bisectors over there, this current is going to be I hysteresis plus eddy this one is going to be Im, because they both are in quadrature, because one is inductor current, other one is the resistor current. This angle is called as theta naught, and when you are going to take this cos theta naught, this is actually the power factor of your transformer. I'm not just going to write TR for your transformer. So the power factor of transformer at no load, and this is going to be a smaller value because the theta naught is there. But when in this case you are going to attach a load over there, then this I naught is just going to be like just 5 or 10% of the overall rated current of your transformer, and certainly when you have a source applied over there. Similarly, you can transfer this all side 2 on that side, but this time you are going to actually multiply it by 1 by a square. So every value is going to be, so you can refer it to your primary side or refer it to the other side easily, anywhere, very easily. So these are some of the losses, some of the IM hysteresis losses, eddy current losses. Sorry, this is the eddy and hysteresis losses of your transformer. And I hope you still have an idea that how this V1, I phase and all are done over here. And similarly, without going in much detail again over here, when you are going to try to do an open circuit test, this means that you are actually going to rub this off overall, and you are going to just have it open circuit. And here, over here, you are going to supposedly attach a small device, which is going to be a watt meter, and that watt meter is actually going to measure the amount of power losses which are happening inside this element and this element also, because the only current path flow is this one. So what is happening, you are only having the process, but since that current is just 5 to 10%, so the I square losses which are happening inside this resistance, we kindly ignore them. So this watt meter reading is going to be giving us the core losses which are happening inside the core, which are the eddy and hysteresis losses, and we call them as the simple core losses. And since they are working at a constant voltage, they will be constant. Then the second case over there, when we are going to effectively short circuit it, and this time we are going to give a reduced voltage. Now this reduced voltage in such a way, because here this branch, this one is very large impedance, because this is a very large impedance resistance, this is a very large AXM. So major current flow is going to come from here to back here. So the only current that is going to flow approximately is just inside this RP and this A square RS. So now this time the watt meter is going to measure you the copper losses over here. So the copper losses, and they will be certainly be variable. Why? Because this is depending upon I square R, and that I square is going to be certainly constant in this diagram, but not constant in this one, because here this is I1, the other side this is I2. But if you have a referred diagram on any one side, you can take the current same. Certainly the impedances are changed in over there. So by open circuit test, you can find out the core losses. By short circuit test, you can find out the copper losses over there. And if you plot these over here, supposedly, let me just plot this over here. I hope you still remember this one a little bit. The copper losses, the core losses, they are constant. So this is WCU core, copper losses. And supposedly this is from 0 to 100% load. So if I have this, supposedly the core losses are constant, and if I want to plot supposedly the transformer copper losses, they are going to actually go on like this. Why they are increasing in exponential? Because this is I square R. So this R is actually going to be R equivalent, and this R equivalent is equal to RP plus A square RS, just like this resistance plus this resistance. So these are exponentially increasing because of the current. So when the current is increasing, you are having this thing. Now what this means actually, when I have drawn this one, this is 12 copper over here. So now when I am going to actually draw the, this is very important point over here. So if I have this one, the efficiency chart is going to be somewhat like this. So this is my efficiency chart. So my maximum efficiency is going to be at a point. So maximum efficiency is going to be at a point when copper losses are going to be equal to the core losses. Why this is so? I'm not going to go into the proof of this one. I guess you still remember from your machines course that whenever the constant losses are equal to the variable loss, that is the point here. At this point, the maximum efficiency is there. And for this particular reason, now listen to this very carefully, for this particular reason, that whenever you have the copper losses in a distribution transformer, you keep those copper losses almost and the core losses something near about that 70% mark every time, because the distribution transformer, when it is working for 24 hours a day, for major time, it's not going to work. In fact, 70% may be a large value. It's not going to work above 40 to 50% over there. Because in the morning time, when everyone is not at the home and you have a transformer near your home, so they are not going to work for in this region, maybe like 40 to 60%. So for the maximum efficiency, they keep the core losses and the copper losses of a transformer nearly at 40 to 50% of the full load. So the maximum efficiency point here, this is, you can call it at, this is approximately at something 70% point. So it's maybe a little large. But whenever you are designing a transformer, you keep this maximum efficiency point somewhere here in this region from here to here, so that the transformer works at maximum efficiency, because the distribution transformer is a liability on the utility company. So you need to actually make it as efficient as possible. But when you are going to design a power transformer, you are going to make this curve more shifted on towards the full load side, because the power transformer, when it is working, it's supplying the power from the generator, and that generator is working at almost the full power. So you have to have it designed for maximum efficiency also. So this is a design work for the designer, that how you are going to actually have that designing done, so that the core losses, and they're certainly in the designer control. We will design it and you will understand this a lot. So this is a little bit, go through this one on the transformer part over there, and just few more questions remaining, and then okay, sorry. Okay, so just few more questions, and now there is a phase lag introduced. In fact, let me go on towards the back this diagram. I guess this is very simple. A transformer is a series device. By word series, I does not mean that they are actually connected in series. This means that there is a power source, and that power source supposedly can be 11 kV. And on the other side, if you have this a load connected, let me just take off this one, and certainly there is a load connected, and that load voltage is supposedly connected at 230 volts. This is a single phase equivalent circuit for a three-phase transformer. So certainly this is not going to be 11 kV. The phase voltage is going to be something 11 kV. If it is Y connected, certainly on that side, or delta connected, then this will be 11 kV. So 11 kV to 230 volt you are actually having. But this JXP and this A square JXS, they are going to have some phase lag introduced. So the voltage waveform, if you measure it here and if you measure it here, keeping the magnitude ratio and all that, there will be a little slight phase lag. So this phase lag is going to come on from this JXP and that A square JXS over there. So this phase lag for power transformers or for distribution transformers, it's not a big problem. But when you are designing a current transformer, because we have talked about the transformer types a little bit in your machines course. So when we are talking about the transformer types based on their usage, I am talking about a CT or PT. This is very much important. Or it can be either a power transformer or a distribution transformer. It can be an isolation transformer or maybe a coupling transformer that you have done in your electronics, but they are very small ratings. So I'm more concerned about a power transformer or a distribution transformer over there, or a CT or PT. But in a CT, since what you are transforming the current. Now, since your power protection course is also going on, your teacher, I guess Sir Bilal is teaching that. So Sir Bilal is going to talk a lot on that phase lag. So when he has discussed a little bit on that phase lag, then we will discuss its effect on our design also, because keeping JXP and JXS is actually our in control, but certainly when you are going to decrease their values, the cost of insulation, the cost of the transformer is going to increase a lot. So in CT, you don't want the value to be phase lagging a lot. Otherwise, your measurement for short circuit current is going to be problematic, because supposedly you have a transmission line, and on that transmission line you have a CT attached over there, and you are measuring it, and supposedly there is a fault, and that fault, supposedly the current was going on and it shooted up and then came down or something. But when it is going to come down, when you are actually going to break off that transmission line, and how you are going to do it, because the CT has to actually detect it. So if there is a phase lag, it's not going to detect very fast. So it's going to have a very problematic or catastrophic problem. So the phase lag introduced by transformer is very much important over there. Then coming on to some more questions over there. Core material, we will talk about in much detail over there afterwards, but normally the material that is used is you are already familiar with this one, is a ferromagnetic material. But the normal material used nowadays in Pakistan is called as CRGO silicon steel. And this is a steel which has some silicon crystals embedded inside it. This is called as cold rolled grain oriented silicon steel. This is cold rolled. Now, as the name suggests you, that what does cold roll mean? That you have a steel sheet, and on that you have a silicon over there, and then you are rolling it on it in some certain direction. Now remember, whenever you are designing a material, and supposedly you want to make a core, okay, and that core has to be supposedly this is one core of the material. So you want inside this one the silicon in this shape. Why you want in this direction? Because the flux, when it is going to move, it is going to move in one certain direction. Either it is going to move in this direction, or either it is going to move in this direction. It's not going to move trajectory. So when the domains are aligned, the material silicon inside it, and it is going to be aligned in some certain direction, you're going to have less eddy currents or less hysteresis losses. Over here, hysteresis losses are going to be controlled. So the material is very much important. And one thing which I missed in the very start also, that transformer is the only device in electrical engineering which can achieve 99.9% efficiency very easily, if it is designed very carefully, and if it is working at some point of load. Not certainly at 10% or 20% of load, because the max efficiency curve is not there, but it can work at 99. There is no other device nowadays. Some converters, power electronic converters, they are reaching an efficiency of like 98 to 99%, but still power transformer is the only device in electrical engineering which has the ability of having a higher efficiency. And if you want to achieve a higher efficiency, the only thing possible is that you have to design a better core, you have to design a better winding, less resistance, and all other problems. Now, designing a transformer and fabricating it are two totally different things. Why? Because in transformer, certainly in Pakistan, you have an 11 kV, and that 11 kV is being converted. Now I'm talking in terms of three-phase. So this is a three-phase delta connected, and this is Y connected. So this is 11 kV / 400 volts. So when you are actually designing a transformer which can withstand 11 kV, the winding is not just the problem. The problem is the insulation. So whenever you are designing a transformer of this much value, the insulation is going to be very much important, so that the primary winding and secondary windings, they don't have any leakage currents through them. And why leakage currents are a problem? Because those leakage currents, they are going to flow through the oil of your transformer. Now, the normal transformers you buy from Hall Road, they don't have any oil inside it. But you have some oil inside any of the distribution transformers or power transformers. Now, the oils which are outside your transformers outside your homes, they don't have any oil inside them. Oh, sorry, they have an oil, but they don't have any mechanism for the flow. So the only mechanism of flow of their oil is convection, and for that purpose you have the fins over there or tubes over there or the radiator over there, which is radiating the heat. The hot air goes up and then it cools down and then comes up the hot oil actually. So the oil, when it is there inside the tank, there is going to be leakage current. And what does leakage current do? Leakage currents give rise to small partial discharges. Now, what is a partial discharge? This is a very whole lot of thing, and many final year projects are possible inside this domain of partial discharges. What does that partial discharges do? The oil decomposes. Their ions are made, currents start to travel. So this means certainly there is some current being lost. It's not traveling from the one winding to the other. Now it's traveling through the oil, through some other medium between the two windings or towards the ground, because the transformer which we are using outside our homes, they have their wire connected to the ground. So certainly this means there is going to be some current flowing towards the ground over here. So that is being lost. So efficiency is being lost. So that current is going to give rise to ions, and those ions are actually going to have a problem for you in later stages. So a time will come that the transformer dielectric strength, this is a very, very important thing, that the dielectric strength of the insulations, that insulation can be asbestos, it can be paper, or it can be any other thing, mica sheet or whatever, they are actually going to lose their dielectric strength, and they can't withstand this voltage or even a 400 volt voltage also. So designing a transformer is totally completely different domain, but when you are assembling it, so normally there are many manufacturers in Pakistan, and they are only graded not just because of their windings or whatever, they are graded for their insulation strength. So whenever I am talking about the insulation strength over there, I am actually talking about the transformer, how they are actually having their insulation strength tested. So this is very much important, that how that insulation strength is tested. Now, one test which we normally do in our high voltage lab, which you will study in your high voltage course also, is this, that you apply an impulse. Now, this is not that impulse which you have been studying in your signal and system course, from which you have been running a lot. This is an impulse which goes on to a very high speed up and then comes down. Now, if it's an 11 kV transformer, now listen to this very carefully. If it is an 11 kV transformer, we give on one of its phase, this is from 0, this is that 50% mark, and this time up till from here to here, this is supposedly 50 microsecond, and up till this point, this is supposedly, I'm not going to do the details of it, that let's just call it 1 microsecond. It's not drawn according to the scale. So when you're going to design a 11 kV transformer, that transformer has to come in our high voltage lab, or maybe some manufacturers now have their own testing labs over there. So they give a 1/50 microsecond impulse to that 11 kV transformer with the peak rating of approximately 95 kV plus. That is the standard. It withstands 95 kV impulse of 1 microsecond/50 microsecond. Now this is the rise time, this is the fall time. Fall time starts from this one. You can't call it a fall time actually. This is actually a nomenclature done in high voltage engineering, that for up till the 50% of the wave from the start, this is called as the 50 microsecond time, or this is called as 1 microsecond. Some standards also make it as 1.2/50 microseconds also. So this one and this one, if it withstands, what will happen, you will going to see on an oscilloscope. Maybe we can ask the high voltage lab if they are doing some testing over there. So if it can withstand, you will see on the oscilloscope the same waveform, because what is the dielectric strength of the transformer? It's actually simple capacitor. And you all know in a capacitor, the dielectric is actually the medium between the two plates. So in a transformer, if you are applying an 11 kV on one of the windings, then the windings can withstand it and the insulation can withstand it. It means it's a good capacitor. So, but if it can't withstand it, supposingly it does not withstand it, then what will happen, what you are going to see, supposingly it will follow this trajectory and then afterwards it will die down like this. Or maybe it goes on a little up and then it dies down like this, because it can't withstand it. If can't withstand it, it will be a dead short circuit. So the capacitor will be shorted and the transformer will be then not usable, or maybe this not usable, can't you be use the word over here, but this means that the insulation strength is not good and there can be a flashover. These two are flashovers. So this is also a transformer testing which is normally done for any of the transformers for 11 kV, and certainly for every 11 kV transformer that is built, you have to get it tested over there from some laboratory in our high voltage lab. We have this facility of testing that transformer over here, and you have to get a certificate for that. Supposedly there are like 100 transformers in one batch. You have to select 1 or 2 transformers. Maybe some company has to select it. Whoever is buying, Vabda is buying it, so they select those 2 transformers from that batch, and then they get it tested at high voltage lab, or maybe I guess Spell manufacturer, the third party, they have also a lab over there, and Vabda accepts their report over there also. So this is some insulation strength testing we will talk about in a little detail, not very much detail, because this is our not domain for this course. Our domain is the design of a transformer, not the insulation strength. But we will talk that how an equivalent circuit can be more good, equivalent circuit can be made by having the issues solved over there. Then there are some questions left over there. I'm just going to leave them towards you. And why transformer grounding is important. This is very much important. So why grounding is important for you. Please go through this one yourself, this transformer. You have done your power system analysis course, like power system operation course over there. Grounding, very much important for your power systems protections course also, because you're doing that one as well. In fact, all the line ground losses or ground losses which involve the ground, they have the grounding of a transformer, very important part over there. And second thing which I want to ask you is the percentage impedance, how that is calculated, how percentage impedance is calculated, and how per units are calculated. This is very much important, because when you are designing a transformer, you have to convert them into your percentage impedance or per unit values over there. So, and I guess the third question, which is very much important, we have discussed a little bit also, that how frequency and voltage are linked for any transformer design. So almost like there's just 2 or 3 questions I have left over there. I will share that word file with you also. So this is some questions. I've given a little brief overview of a transformer. We discussed the equivalent circuit. We discussed the maximum efficiency curve. I talked about different types of transformers, CT and PT. For CT and PT, when time comes, I will discuss a little bit in depth on CT when we've done the transformer design, because this is a very expensive device. A simple CT, just for your information, this is working at 11 kV. Approximately, I guess 1 year or 1.5 years back, even 2 years back, the cost was approximately 35 to 40k rupees. This is one transformer. So you can understand how this is going to be a problem for designers, because if it fails, all that money is lost. So we talked about that inductance, we talked about the Lenz's law, we talked about how the core losses, how the transformer flux remains the same. Then we have talked about how the losses are changing. Then we have talked about the single phase, 3-phase shell and core type transformers. And then we have talked a little bit on this hypothetical transformer also. So this is all about DEM and or electric machine design over here. This was an introductory lecture. Please kindly revise your transformers over here, whatever we have done today. And hopefully in the next lecture, I am going to talk on the transformer first design equation, which is actually equal to E equal to 4.44 F phi n. So we are going to design this first equation. I'm going to prove it by like 2 different ways. And the books are the same. Indra Jeet Das Gupta, that is an Indian author. It's a very good book for distribution transformer design, even for power transformer design. And as far as the other book is concerned, which is the Principles of Electric Machine Design, we are going to do a lot from that book. I will advise you to strongly get that book from Urdu Bazaar. It's an old book a little, but still very much better, because machine design and transformer design, they have not changed that much. So you can see those book names from your course outline. So that will be all for today. I hope you enjoyed it, and let's meet in the next lecture. Thank you.